Here, just to review a little bit, Bronsted-Lowry concept. Okay, first, a base is a species that accepts protons. Hydroxide is only one example of a base. Okay, you may have acids and bases that have nothing to do with protons or hydroxide ions. Acids and bases can be ions as well as molecular substances. Okay, remember we talked about carbonate being a base or ammonia ion being an acid. Okay, so acids and bases are ions as well as molecular substances. And we talk more about that as we go on with the semester. Acid-base reactions are not restricted to aqueous solutions, but most of what we will do will be aqueous solutions. That's why we're going to concentrate on Bronsted-Lowry. Okay, you can have other solvents, but if you have other solvents, then things that are acids and bases as we know it will not be acids and bases anymore. Okay, depends on what that solvent is. Some species can act as either an acid or a base, depending on what the other reactant is. Molecular species that we call acids and bases will always be that in water. So if I know it's an acid in water, it will always be that. If it's a base in water, it would always be be a base in water, where water will be the other. Okay. One species is an acid, then water is going to be a base. If the species is a base, then water is going to be the acid. The third definition of acid bases that we want to discuss was Lewis' concept, and I want to discuss that because it's important. You use it a lot when you move on to the next chemistry, organic chemistry. Not so much in this class, but when you get to organic chemistry. Lewis' concept defines an acid as an electron pair acceptor. Okay, so an acid as electron pair acceptor, and a base as makes available electron pair. Okay, so what's happening here is we're just looking at electron pairs. We're not looking at hydrogens, not hydroxides, just electron pairs. And by definition, an acid accepts a pair, a base makes available. Now, many books may say that a base is something that donates a pair. I kind of tend to steer away from that definition, because to me, if something's donated, it's not yours anymore. And basically in this case, what we're doing is just basically sharing those electrons between those atoms. This concept broadened the scope of acid-base theory to include reactions that don't even involve H+ to be acid-base reactions. The Lewis concept embraces many reactions that we might not even think of as being an acid-base reaction. To me, this is the most useful and universal definition. However, it involves looking at Lewis dot structures, which takes a little bit more work. So the easiest thing in aqueous solutions is dealing with just looking at protons, is why we use that one for the most part in this chapter and the chapters to come. But once again, these theories are complementary. If I do it on this basis, it'd still be an acid in Bronsted. It'd still be an acid in Arrhenius if I can use those theories to make my decisions. Here's an example. Got boron trifluoride reacting with ammonia. Okay, BF3 and NH3. These are two components that react with each other to form a new compound, a coordination compound. Okay, it's a complex. And what we're looking for is lone pairs, what's bringing it and what's sharing with it. As you can see with ammonia that it's coming over with a lone pair, and boron is then coming to share that pair and form this new bond between boron and nitrogen. So by definition of Lewis acid-base definition, since NH3 is bringing the lone pair with it, this would be my base, or sometimes referred to when we talk about coordination chemistry, the ligand. Okay, we'll combine with that boron, the BF3, which is the acid component. So boron trifluoride accepts the electron pair, so it is the Lewis acid. Ammonia makes available electron pair, so it's the Lewis base. As I said, I believe this is the most important concept. However, we won't be using this as much in this class because we're dealing with aqueous solutions. But it's something I wanted to introduce you because you will be using it when you get to organic chemistry. What we're going to talk about now is relative strengths of acids and bases. I want to be able to look at an acid, compare it to another acid, and see which one's a stronger acid. Bronsted-Lowry concept introduced the idea of conjugate acid-base pairs in proton transfer reactions. We consider such acid-base reactions to be competition between species for hydrogen ions. Basically, we're competing for that hydrogen ion. The one taking on the hydrogen ion is a base, the one giving it up is an acid. So there's a competition there. The stronger acids are those that lose their hydrogen ions more easily than other acids. Basically, they donate their proton quicker. So stronger acids are things that tend to lose their hydrogen ions easier. Okay? We're putting more acidity in solution, therefore we're looking at a stronger acid. From this point of view, we can order acids by their relative strengths as hydrogen ion donors. The more that they want to donate the proton, okay, the stronger the acid. Okay, the easier it is to ionize that hydrogen ion and make more acidity in the solution. Similarly, we can look at it in terms of bases. The stronger bases are those that hold on to that hydrogen ion more strongly than other bases. Therefore, it's harder to lose a proton. So the harder to lose the proton, the stronger the base. Or putting it in bottom line nutshell type thing. Easier it is to give a proton, the stronger the acid. Harder to give up a proton, the stronger the base. So giving up that proton easily, stronger the acid. Giving it harder to take off that proton, stronger the base. Now, if an acid loses its proton, its resulting anion is now in position to reaccept the proton, okay, making it a Bronsted-Lowry base. Okay. It's logical then to assume that if an acid is considered strong, its conjugate base, that is, that anion, would be weak, since it's unlikely to accept that hydrogen ion. It wants to donate that proton as soon as it accepts a proton. Okay, what I want to do is show you this in an example so you can understand what I'm trying to say here. Let's look at HCl. That's a strong acid, right? Plus water. It will now form hydronium ion and Cl minus. Okay? Now, according to our Bronsted-Lowry theory here, Cl minus is a base. It's the conjugate base of that HCl. Well, what does a base want to do? Well, it wants to take on a proton. Okay, so I basically can take this Cl minus, and we can rewrite that now. Cl minus now is a base with water. Okay, it can now accept that proton, and now it forms OH minus plus HCl. Okay, so if Cl minus is a base, then it's going to want to accept the proton, being its basic character, and form OH minus and HCl. But let's analyze now where we stand at this point. HCl is what? Well, HCl is a strong acid. What happens to a strong acid? Well, that breaks up. It's going to break up into hydronium ions plus Cl minus. Okay, so far looking at that second reaction, I'm forming OH minus, H3O plus, and Cl minus. Well, OH minus, I got 1 mole of that and 1 mole of H3O plus. Mole to mole, 1 to 1, that neutralizes itself, so that's canceled out. So all I'm left with is Cl minus, which is what we started at. Okay, so in essence, what we're saying here is that conjugate base has no affinity for that proton. Basically, we're going to be back to where we ought to start with. So it's extremely weak base, so extreme that it's not even going to show any appreciable attraction for that proton. So in essence, if we have a strong acid, its conjugate base is extremely, extremely weak, almost non-existent. In other words, the stronger the acid, the weaker the conjugate base. It can't be a strong acid and a strong conjugate base. Okay, so if it's a strong acid, it's got to be extremely weak base. Okay, which gets us to the following statement, which we can use to compare acid strengths. Okay, the stronger the conjugate acid is as an acid, the weaker its conjugate base is as a base. Okay, the stronger the conjugate acid is as an acid, the weaker its conjugate base is as a base, or vice versa. The stronger the conjugate base is as a base, the weaker the conjugate acid is as an acid. Okay, so if it's a strong base or a strong acid, its conjugate species is extremely weak. We can use this to make decisions. Example. Okay, HCl, HCm. Okay. What I want to look at is the Cl minus and the Cn minus. I want to know which one of these is the stronger base. Right? Is Cl minus the chloride ion or the cyanide ion? Which one of those is the stronger base? Using the statement above, I can make that decision. Okay, let's think about it. I got HCl plus water gives me hydronium ion and Cl minus. What is HCl? HCl is a strong acid. Okay, it's a strong acid. So what happens to the base characteristics of the Cl minus? Well, it's an extremely weak base, almost non-existent, as I showed you a minute ago. What is HCN? That's a weak acid. Okay, if it's a weak acid, then what kind of strength do we think Cn minus is going to be as a base? Well, it's going to be some moderate strength to base. Okay, so looking at this information, we said the stronger the acid, the weaker its conjugate base. Since HCl is a strong acid and HCN is a weak acid, okay, that would tell me then that Cn minus, the cyanide ion, is a stronger base than Cl, based on that statement above. Okay, HCl is a stronger acid than HCN. Therefore, Cn minus is a stronger base than Cl minus. Okay, so the answer is Cn minus. The cyanide ion is my stronger base. That's my stronger base. And cyanide ion is my stronger base. Well, it's easy to determine strengths between something that's a strong versus a weak. Okay, so we can just look at our conjugate base and make that decision, just like we just did just now. But what happens if it's the same class? What if I got a strong versus a strong, or a weak versus a weak? How do I decide which one's going to be the stronger acid or the weaker acid? Okay, how do we determine that? That's what we're going to talk about next. Okay, how do we determine the strength of acids and bases that are in the same class, meaning all strong or all weak? Well, there's two factors that are important in determining the relative acid strengths. Okay, first one deals with polarity. Okay, the polarity of bond to which the hydrogen atom is attached. Okay, you might recall if we have a lone pair, that's as your bond, you get a lone pair. Okay, between two atoms. They don't share the atoms equally if they have different atoms all sharing those electrons. Okay, the species that has more electronegativity is going to get a bigger share of electrons, and what's going to happen is it's going to have these electrons to spend more time along the more negative species, okay, and less time around the positive species. So what happens is you get a dipole moment, this delta minus. Okay, you get an excess negative charge around that more electronegative atom, and you get a delta plus. Okay, the electrons are spending less time around that species, so that you get an excess of positive charge on that species, hydrogen in this case, and that's all based on electronegativity. Remember, the trend on electronegativity is that fluorine is the most electronegative, so it's increasing to the right and increasing up, pointing toward that fluorine being the most electronegative. Okay, so as this electronegativity difference occurs, the more that this change in electronegativity occurs between those charges, the harder it's going to be to hold on to that hydrogen. Okay, as electrons are drawn more and more to that X species, then it's going to weaken that bond more and more, and it's going to be easier to pull off that hydrogen. So the larger that electronegativity difference is, the weaker that bond is, the easier it is to pull off that hydrogen, the more acidic it's going to be. The more polarized, meaning larger electronegative difference, the bond, the more easily that proton is removed and the greater the acid strength. Okay, so the larger that electronegativity difference, the easier it is to remove that proton because more of the electron is going toward that X species compared to the hydrogen, spending more time around the X than it is the hydrogen. Therefore, the easier it is to pull off that hydrogen. Okay, therefore more acid strength. Okay, more H plus in the solution there. The second factor is the strength of the bond, or in other words, how tightly is that proton being held. This depends on size. Okay, once again, okay, let's look at HX here. Okay, let's think about it. If I have a species that has atom this size, let's say, okay, where you know that the charge is in the middle of the nucleus, you got a negative there, charge of some sort, okay, and you have your positive charge on your hydrogen. Now let's compare that to something that's larger, okay, which now the negative in the nucleus is somewhere in the middle there, okay. As that species gets larger, okay, are we going to have more attraction for that hydrogen or less attraction? Well, the larger that species is getting, the radius of that species is getting, the further away it's getting from that hydrogen, the easier it's going to be to pull off that hydrogen, okay, because it's not as attraction. Attraction is that plus and minus being attracted to each other. So as this species is getting bigger and bigger, then I'm getting more distance between the charges. It's going to be easier to pull off that hydrogen. Okay, so size matters here. The larger atom X, the larger the atom the X, the weaker the bond, and the greater the acid strength. There's less attraction between those atoms, therefore it's easier to pull it off. So as that species is getting bigger, it's getting further away from the hydrogen, I can pull off the hydrogen easier, therefore it's going to be more acidic, larger acid strength. Do you recall the trend on size? Okay. Well, the trend is basically going down and to the left. Okay, this is your radius. Increasing, the opposite of the electronegativity. Okay, pointing in the other direction. Here are your larger atoms. Okay, down at the bottom there. Bottom left-hand corner. So, bottom line, okay, the larger the electronegativity difference, the larger the size of the anion, the stronger the acid. The easier it is to pull off that proton. Okay, so bottom line, larger the electronegativity difference, larger the size of the anion, the stronger the acid. The easier to pull off that proton. These are the two things you look at to decide which species is a stronger acid. Now, for the majority of the time, the one that's going to rule the most is going to be electronegativity difference. Okay, size is only going to matter when we're talking about going down the column of a group. Okay, which we're going to do that exercise first, which will be on the next slide. Okay, but the majority of the time, it's electronegativity difference is the main factor. Okay, we'll show you about size, and as I said, on the next slide. Let's consider a series of binary acids, binary meaning two species forming an acid, and we're talking about going in a column of elements. Okay, now on your periodic table, okay, you have your rows. These are all basically, as you go down the periodic table, you're adding on a shell. Your shell's getting larger and larger and larger as you go. Okay, you're adding 8 electrons, and your shell's getting bigger every time you go through. Well, electronegativity is not changing as much going up the periodic table. It changes by a smaller increment compared to the size that you get by adding a whole shell every time you're going down the periodic table, following a column. Okay, so we're getting, you got one shell, then you got another shell, then another shell, and another shell. You're just getting bigger as you go down that periodic table. So what's going to matter is going down the column is going to be that radius. Okay, it's increasing markedly and dictates the result. Okay, more so than the electronegativity. So let's look at HF, HCl, HBr, and HI. Okay, I want to figure out which one of these is the stronger acid. Now, I want you to realize when I say what's stronger or strongest, it's in comparison to the species I'm looking at. Just because a species is a stronger acid compared to something else, that doesn't make it a strong acid. Okay, remember, strength is based on ionization. When we say something strong, it's ionizing 100%. But I can compare relative to the other species. This one's stronger than the other one because it's ionizing more than the other species. Okay, so getting back to my example here. On your periodic table, okay, you have iodine, you have Br, you have Cl, and then you have F. Okay, and that's the way to look on the periodic table. Okay, being that it's a binary species and it's going down a column, I'm going to look at size. Okay, which one of these is the largest atom? That would be the iodine. Okay, next in line would be Br, next would be Cl, and then F would be my smallest. Okay, and that's my smallest. So since HI has the largest anion, that means that the hydrogen is going to be the furthest away from that anion. Therefore, it's going to be the easiest to ionize. Since it's ionizing easier, it's going to be the most acidic. Therefore, HI will be my strongest acid of this group. Next would be Br, then Cl. F, that's my smallest anion, therefore it's the closest to the hydrogen. Therefore, it's going to be the hardest to pull off, that hydrogen. Therefore, it's going to be the weakest acid. Okay, so HI is the largest radius, easiest to ionize, and the strongest acid. Next will be HBr, next will be HCl, and then HF will be my weakest acid. Smallest radius, hardest to ionize. Now, this is just in comparison to these substances. It's not necessarily a comparison to these substances in water. What do I mean by that? Let's look at the species involved here. HI, HBr, HCl. Do you recall what those are according to our list of acids as strong versus weak? Yes. HI, HBr, and HCl are all strong acids. These are all strong acids, while HF is a weak acid. Well, what is the definition of a strong acid? We basically say if it's a strong acid, it ionizes 100%. Well, if HI ionizes 100%, HBr ionizes 100%, and HCl ionizes 100%, does it really matter about the size of the radius when I'm comparing those three? Well, no matter what I have, it's ionizing 100%, so they're all ionizing the same. So in essence, really what I should have written for an aqueous solution is that HI equals HBr equals HCl because they're all strong acids. They're all breaking up 100%. Ionizing, okay, or greater than HF in aqueous solution, okay. In some other solvent, I might see HI greater than HBr, greater than HCl, but in aqueous solution, we get HCl, HBr, and HI looking very similar, okay. They all ionize 100%. It doesn't really matter the size of the species, okay. This is getting us to another concept called the leveling effect of water, okay. So let's talk about that. This acid strength for the strong acid does not hold true for water as a solvent. Remember that we discussed earlier that some acids are strong and others are weak. The strength is related to the amount it ionizes. And that's important to realize. Anytime we're talking about strength, it's basically on how much it ionizes. Strong, 100%. Okay? Strength is based on ionization. In water, the strong acid base ionizes 100%, meaning that these species break up 100%. All these acids look the same in water, which we refer to as the leveling effect of water. All these species look exactly the same. The tendency of a solvent to accept or donate protons determines the strength of a solute, acid, or base dissolved in it. The strong species all completely ionize and are all the same strength. I'd like to show you this by doing an example here. Show you what I mean. HCl and HBr. These are both strong acids. Okay, they both break up 100%. They both ionize 100%. So if I had a 1 molar solution of HCl and a 1 molar solution of HBr, how much HCl do I really have in solution? Well, we said ionizes 100%, so therefore I have no HCl. How much HBr do I have? Well, once again, it's a strong acid. We're saying it breaks up 100%. So once again, we're saying there's no HBr. But if I started off with a formal concentration of 1 mole HCl, then how much hydronium do I have? Well, it's a 1-to-1. Therefore, I got 1 molarity of hydronium. HBr, same thing, formal concentration of 1 molar. Well, it's a 1-to-1, so I got 1 molar of hydronium again. What do you notice about the species in both cases? Well, I have exactly the same strength of hydronium, 1 molar and 1 molar. They look exactly alike. So in essence, what we're saying here is the strongest acid that's available in water is the hydronium ion, because all the strong acids break up 100%. What then is the strongest base in water then? The hydroxide ion. All the strong bases break up 100%. So this is what we mean by the leveling effect of water. Okay. Therefore, the strongest acid in water is the hydronium ion, and the strongest base is hydroxide ion. Now, you must realize, though, in another organic solvent, you may find, based on bond strengths, radius, that HBr would ionize more, meaning easier to break off that hydrogen, than HCl, and is therefore truly the stronger acid. However, in water, that's not what we see. There's no difference in ionization, therefore the same strength. Hence what we refer to as the leveling effect of water. Okay, all those strong acids look exactly the same. Okay, but based on those molecular species, we could see that HBr would ionize more than HCl based on the size of Br compared to Cl. All right, let's talk about comparison of acids going across, okay, in a row of elements, okay, what's going to make the difference of what's going to be a stronger acid compared to another one. Well, in that case, when we're going across the periodic table, it's going to be polarity, because the electronegativity is changing a lot more than the size, because basically we're not adding a shell to it. We're in the same row, therefore we got the same shell. Okay, if we're in the second level, then we always have that number 2 level. We're just adding electrons as we go across, and protons. Okay, but we're not increasing in size. Okay, so what happens is polarity is going to dictate and be the dominant factor. As electronegativity increases going to the right, the polarity of your HX bond increases by a larger amount. Remember, it's increasing going to the right electronegativity as compared to the change in size in the acid strength increases. Okay? So let's see if we can look at some. Looks at H3N, H2O, and HF. I don't want to predict as the acid strength here which one would be the stronger acid. Now, H3N, H2O, and HF, we're talking about all being in the same row. Okay, you're looking at the same row. Looking at the same row. So you have nitrogen, oxygen, and fluorine all in that same row. Okay, we're saying that size isn't going to matter here. What's going to dictate here is polarity. And as I said, most of the time polarity is what's going to dictate it. Okay, exception really being that binary going down a column. So if we look at electronegativity, which of these is the most electronegative? Well, that would be fluorine, followed by oxygen, followed by nitrogen. So the greatest electronegativity is going to be between hydrogen and fluorine. Next will be oxygen and hydrogen. And then next would be nitrogen and hydrogen. Okay? So then, based on that fact, okay, there's a large electronegativity difference, therefore it's going to be easier to take that proton off of that HF compared to the other ones, therefore it is the strongest acid. It is not a strong acid, it is the strongest acid between these three. Okay? Then H2O will be next, and then H3N will be final, will be the last one. Okay, because it has a smaller electronegativity difference, therefore it'll be harder to pull off those protons, and therefore it will be the weakest acid between these three species. Notice this is why HF is always an acid in water. Okay, based on this fact right here, HF will always ionize more than water. It'd be easier to pull off that proton, therefore HF will always be an acid in water because of that fact. This is also why H3N will always be a base in water. Now, you may look at that and not recognize that compound, but let me rewrite that a little bit and see if you notice something. Okay, H3N is NH3. We don't write it H3N. Why? Because it's never going to be an acid in water. It's always a base in water. Based on this fact, due to the electronegativity distance being so small, it's harder to pull that proton off compared to water, pulling off the proton. Therefore, ammonia will always be a base in water. Hence the reason why you rewrite it NH3 instead of H3N, because it's never going to be an acid in water. Okay, let's look at some oxyacids. Okay, an oxyacid has a structure of hydrogen, oxygen, and then some component. Okay. The acidic hydrogen atom is always attached to the oxygen atom. That's the one that we're looking at. As you go back, you remember we talked about acetic acid. Okay, that is my acidic proton, the one attached to the oxygen. The other ones are attached to carbon, so they're not acidic. Bond polarity, once again, bond polarity is the dominant factor in the relative strengths of oxyacids. When in doubt, think about polarity. Okay, as I said, the majority of the time, polarity is going to make the difference. This in turn depends on the electronegativity of that wide atom. So we're looking at this Y atom as to the electronegativity to decide, okay, acid strength. How much pull does that Y have on that oxygen? Okay, the more pull, the more electronegativity, the more I'm going to pull this way, which then weakens this bond and allows that hydrogen to come off. Okay, so the more electronegativity on that Y, the more it's going to pull on that oxygen, and then we're going to weaken that bond and allow that hydrogen to come off more easily, making it more acidic. If the electronegativity of Y is large, then the OH bond is relatively polar, and the acid strength is greater. Therefore, it's easier to remove that proton, and therefore it is a stronger acid. Let's predict the following order of acid strength: HOI, HOBr, HOCl. We won't be looking at size, we'll be looking at electronegativity. Okay. Okay, of these, which one has the most electronegative atom? Okay, the hydrogen's attached to that oxygen. Okay, so there's no difference in bond size. Okay, I got hydrogen, oxygen, hydrogen attached to oxygen, hydrogen attached to oxygen. So there's no size difference, so I'm not going to look at size. So the only real difference between these species is that Y component. Okay, so that's adding electronegativity. So we got to look at that electronegativity to see how it's going to pull on that oxygen and weaken that bond to allow that hydrogen to come off easily or not. Well, electronegativities. Okay, we're looking at chlorine, bromine, and iodine. Okay, so chlorine is the most electronegative. Okay, remember the trend over and up. Okay, chlorine is the most electronegative, followed by bromine, followed by iodine. Since chlorine is the most electronegative, then it's going to pull more on that oxygen, okay, weakening that bond, which is going to like more hydrogens being able to be removed. Therefore, it's going to be more acidic. Iodine is the least electronegative, so therefore it has less pull. Therefore, it's going to be producing less hydrogens, which means it's be the least acidic in this group. So, larger electronegativity due to that chlorine, easier ionize, stronger the acid. Be stronger than HOBr. And then HOI, smallest electronegative difference, therefore the hardest to ionize, therefore the weakest acid. Okay, we're just looking at that Y component because the fact HO those are the same in all cases. So there's no size difference between the hydrogen and oxygen atom right next to it. Okay. So the major difference is this Y and how it's going to affect that oxygen. Okay. Weakening that bond or not. Now, with each additional oxygen, you add more electronegativity. So Y becomes more electronegative. So if I keep adding oxygen, what's going to happen is we're going to pull more and more and weaken that bond more. So hydrogens are going to be released more. So as a result, the hydrogen atom becomes more acidic as more oxygens are on the species. The acid strengths of the oxy acids of chlorine increase in which order? Okay, so you have HClO, HClO2, HClO3, and HClO4. Which one of these is the strongest acid? Which one is the weakest? What we're saying is, since we're adding more oxygens, okay, we add more electronegativity, which is pulling it more in one direction, which is weakening the bond and allowing the hydrogen to come off more easily, compared to the next one, which is HClO3, have 3 oxygens, HClO2 versus HClO. Since this only has 1 oxygen, it has the least pull, therefore it's going to be the hardest to pull off that hydrogen, therefore it's going to be the weakest acid in this group. So the strongest would be HClO4, next HClO3, followed by HClO2, and the weakest being HClO. Okay. Now you might have already been able to tell this because you remember you memorized the strong acids, and HClO4 is one of the strong acids, so don't let any of these rules supersede what you know. Okay, you know the strong acids, so that should be easy to figure out immediately. You should know HClO4 is one of the strongest strong acids, therefore that has to be the strongest one. Now another way to look at this is the charge on Y is changing. Okay, as I'm adding an oxygen, the charge on that chlorine is changing as well. Okay, we have chlorine at the beginning here has a 2+ charge, a +1 charge. Then we go +3, and +5, and then +7. Okay, that's changing because I'm adding an oxygen each time, so it's going up by +2. So as that charge is getting higher, okay, it's going to be more attraction to the oxygens being pulled on them, so it's also going to pull it and weaken that bond as well. Polyprotic species, okay, and that's acids that have more than one ionizable proton, okay. How do we determine which one's a stronger acid in those cases? Okay, each successive hydrogen atom becomes more difficult to remove because the species becomes negatively charged. Therefore, if it's a negatively charged species, it's going to be harder to pull a positive proton off. Therefore, if we look at the acid strengths of this series, H3PO4, H2PO4 minus, HPPO4 2 minus. Okay. As it becomes charged becomes a charged particle here, then basically I have to pull off a positive proton. It's going to get harder and harder as that charge gets higher and higher. Okay, so therefore acid strengths of your polyprotic acid and its anions decrease with increasing negative charge. So looking at this series here, H3PO4 is going to be my strongest acid of the 3. H2PO4 minus is going to be next in line because I have just a minus charge, okay, compared to the other one which has a 2 minus. So it's going to be even harder to pull off that proton off that 2 minus as that charge is getting more negatively charged. So therefore, my strongest acid in this series would be H3PO4, next would be H2PO4 minus, and last would be HPO4 2 minus. Due to that charge increasing as we losing our hydrogens. Homework 25 deals with looking at species to decide which one's a stronger acid. Now realize, as I said before, it's stronger compared to the species it's comparing to, not that it's a strong acid. By definition, strong is 100% ionization. But comparison of the species you're looking at, which one is the stronger one? or the strongest one if it's more than two species. And the majority of the time, if you're in doubt, make sure that you look at polarity first, okay? Size is only going to really matter if you're going down the column and you're looking at binary species.